So OBS thinks like is connected properly?
Yes, OBS says connected and uploading.
Okay. And you're sure you changed you didn't like forget to change the URL, right?
Right, I just tried it twice. Teams just spinning. You can see it starting, it'll fix it for some reason, but
Maybe.
here, I'll just try. I'm gonna get started.
Yeah. Well, at least like something will go live and it'll be a little easier.
Okay, hit start. According to OBS, we're live.
Yeah, but I'll see. Oh, I see stuff. I think they're seeing me right now.
Okay.
All right, let's just roll with this. Hopefully everyone can see me right now. Yeah, cool. Landon told me we are live. So don't spam the Q&A telling everyone we're good. That was a mess last week. Welcome to Recitation. Sorry we started a little late, guys. Just some couple differences from last week. We've got another TA with me here helping out running the stream. That is Tyler. I don't know if you'd be able to hear him if he said hi, but he's going to be trying to make sure we don't have a lot of the AV problems and issues we had last week. Unfortunately, the little trade-off we got with that is Landon wasn't able to be here with me this week, so it's just going to be me teaching all on my own up here. So hopefully things go fine with that. For you guys watching in the 6:30 recitation, fortunately you should have a much more enthusiastic TA instead of me stressed after dealing with 2 hours of technical problems. So that should be a better experience too. But with that said, we're already running a little late, so let's go ahead and get started after making sure. Yep. So can they see this stuff? All right, so just some normal start of recitation announcements. Your homework 2 that was released last Friday, that's the doubly linked list homework. That's going to be due this Friday, the 28th, 11:55 p.m. Homework 3 is going to be released that same day, due the September 4th. That's the next Friday right afterwards. So just another 1-week homework. That homework's about decks. So we'll be talking about those next week in recitation, and you'll see those kind of next week in lecture too. The recitation worksheet for this week, it's going to be your first recitation worksheet. After this recitation, that should be out on Canvas. As a note, it's not the recitation canvas. It's going to be out on the campus and online canvases. You'll be able to see it in the files section on Canvas. I think it's under its own folder. If not, it's under the recitation folder. You should be able to find it without too much trouble. Also, another difference you might have seen in my announcement is we are going to be publishing the questions and answers from the Q&A. So if you go to the Q&A, you should be able to see questions that your fellow classmates have asked and what people's answers were. The little trade-off with this is just with how everything's set up. I'm not really necessarily going to see all these questions while I'm teaching. So some of these clarifications aren't necessarily going to happen live, but they will happen in that Q&A. So make sure you're checking there every once in a while to see what questions are getting asked. With that said, let's go ahead and get started today. First thing I'm going to talk about is a little bit of a recap. It's some stuff we talked about last week, but I know I was having a ton of technical issues at the time, and I think a lot of this was off screen, so you guys didn't really see it. So let's do a brief recap of data structures versus ADTs. What do they really mean? So ADTs are abstract data type. It's just kind of a overall depiction, big picture description of some set of properties or operations. You can think of it kind of like an interface in Java. So some examples of that are we have the list ADT that we've talked about so far. Later you'll see the map ADT, trees and stuff. So all list says is it says, okay, I'm keeping track of some items, they have some order. I can add to the front of it, I can add to the back, I can add at some index, I can get items. That's all it really says. It doesn't specify how I do these operations. It doesn't really specify how expensive they need to be. All it says is that these have to be possible. These are the things I can do. Data structures, on the other hand, these are our concrete implementations. So every data structure has some associated ADT with it that it implements. So we have Arraylist, which implements list. We have linked list, which also implements list. Later we'll see hash map, which implements map. But these are your kind of concrete implementations. These are your actual classes that you would be instantiating and using. So with that said, let's go ahead and start talking about some new stuff. Let's talk about linked lists. What is a linked list? Well, first we should talk about, as I was just talking about with ADTs, we should look at what ADT a linked list is implementing. And as the name suggests, and as I've already said, it's going to be the list ADT. So that's the exact same ADT that Arraylists is implementing. Oh, this marker is starting to die. That's very bad. All right, this recitation might be done out in blue. Okay. That looks like it should be readable. Okay, so, but the differences between a singly linked list and an array list is that we're not using an array anymore to store the data. Instead of an array, linked lists are going to be using nodes to store this data. Now, a node is kind of this class we're creating for the purposes of this linked list. It's not, you shouldn't expect it to have some kind of meaning outside of these data structures. All a node is it stores two things for a singly linked list. It stores the data. So that's going to be just like every index of an array stores a piece of data. Every node in a linked list stores a piece of data. And it has this next node reference. So a decent way I like to think about singly linked list is you can think of it like one of those scavenger hunt things, where you start with some clue that leads you to a location. And you go to that location, you find another clue that takes you to another location. And the only way to go through all of the locations is to get there, look at the clue, and go to the next location. Which means a decent point about all this is that no longer is all of our data contiguous in memory. So with an array, we had all of the data kind of in this one big block all grouped together. But with a linked list, we're going to have maybe like one piece of data here, then like a bunch of random junk. Then we've got another piece of data, then like some more random junk, another piece of data, and you've got like your favorite phone, your favorite number, then another piece of data. You don't know. The point is that you don't really know where each piece of data is relative to the previous. Just like in the scavenger hunt analogy, the only thing you know is once you're at a piece of data, you know where the next one is. But there's no relation between like where these pieces of data are and where these pieces of data are relative to each other. You don't have anything like that. And that's going to change how we do a lot of our operations. Speaking of our operations, I'm going to move over to that. I think you're going to probably need to move the camera over to get this stuff in frame. All right. So when we're dealing with a singly linked list, the only thing we have access to is we have the head, always, we need that. And sometimes we have the tail. So what are these? So the head is the first node in the list. So I'm going to keep using the scavenger hunt analogy because I think it fits a lot of things well. That's your starting point. We know that you start the scavenger hunt from the bottom of the Kolk stairs at Georgia Tech or something. You know exactly where to start. And sometimes you know the tail. You know the scavenger hunt ends once you reach the COC or something like that. But that's all you necessarily know with a singly linked list. And the reason we have this tail sometimes is you'll see it might speed up some of the operations that have towards the end of our linked list, but it's not going to be perfect. There's still going to be some issues that happen even with us having a tail node. But an important detail with singly linked list operations is there's no longer any indexing into data like we had with an array list. So what that means is if I want to go to like the fourth piece of data in the linked list, there's no way for me to just directly go there immediately. The only way for me to get to the fourth piece of data is to start from the head, go to the second, go to the third, then go to the fourth. There's no skipping around, only you can go one by one. Something that tends to look like in code is we tend to see like this structure of code, where we use this kind of current node as our iterating node. So we start it at the head usually. It's very often named like cur or something. And then we have this loop that looks like while cur is not equal to null, we do something with cur. I should specify that's like with cur. So maybe that's looking at its data, maybe that's altering its data a little bit, something like that. And then we have this cur equals cur.next, and that moves us kind of forward by one spot. And once we reach the end of our linked list, the end is kind of defined as the last node has a next pointer that goes to null. So once we reach the end of the linked list, cur will be equal to null, will be past the end of our linked list, and that will indicate that we've gone past all our data. So, and this is kind of like a size blind or index blind method of iterating. So you can still do like your standard for loop strategy that you've seen with array lists and keep track of what index you're at. And a lot of, like in your homework and implementations and stuff, you have like a size variable you can use. There are a couple ways to iterate through linked lists like that. But this is a really common structure you'll see. Now let's go ahead and look at how some operations look with a linked list. So this over here is going to be our little linked list that we use as an example. I've got my notes over there just for how I'm doing everything. So the first thing we're going to do is we're going to add a piece of data into our linked list. When we start with just head pointing to null automatically. I don't have a tail variable in this or anything, just the head. Null is just, so, okay. Something you've probably seen us mention in lecture is this idea of sentinel nodes, and it's in the textbook too. In this class, we're not going to use sentinel nodes at all. A sentinel node would be like a blank dummy node here to indicate where the head is. Nothing like that. If our list is empty, head points straight to null. So when we add our first item into the linked list, what we're going to do is we're going to create that node, populate our data in it. Let's just call it 1. Then we're going to change the head so that it points to our new node. And then our new node now needs to point to null as its next pointer. So when I draw nodes like this, it's going to be this kind of box structure with the data in this big box, and this right little rectangle is going to reference what my next pointer is. So you'll see arrows coming out of that. Now let's do our second add operation. We're going to add something to the front. So I'm going to do add 2 to index 0. Now when I'm adding something to the front of a linked list, it's going to be really easy. All I need to do is I need to create my new node. I'm going to move these over here. I create my new node with my data in it. I set the next pointer of my new node to be equal to what my old head is. Now, as a note, when I say I set the next to the old head, there's kind of two ways a lot of people interpret what that means. They think I'm doing something like this, or I'm doing something like this. One of these two things. The actual answer of what's going on is this bottom arrow. Whenever we set something equal to the head, or set like a next pointer equal to the head, that's not like going to follow the head around every time. All that's going to do is it's going to set it to what the head is at that exact moment in time. So this hooks up to our linked list, and then all we need to do to finish this operation is move our head pointer to point to our new node. So now head is the first node in our linked list, and then that points to our old node, which is now index 1, which points to null because it's the end of our linked list. Now let's see what adding something kind of not at index 0 looks like. Let's say we're going to add 3 at index 1. And I'm going to redraw it down here. So the first thing we need to do is we need to get to where we want to add our item. So for index 1, that's kind of trivial, because all we need to do is get to the index before it, which means that we essentially start iterating. We can use this cur variable like we had over here, point that to our head, and then realize, okay, we're at index 0, and we're trying to add to index 1. That's good enough, we can stop. Then what we do, I'm going to redraw this. We create our new node. I'm going to write it up here. What we're going to do is we're going to first hook our new node up into the linked list. It is very important that we hook the new node into the list before we connect pointers from the list to our new node. And I'll explain the reason why we do that after I do this first example. So the first thing we do is we set our new node's pointer equal to cur's next pointer. So if we follow that, this is our new node, this is cur. Cur's next pointer points to 1. So if we set our new node's pointer to that, it's going to look like that. So now 3's next is 1. After we do that, now we need to hook up 3 into the list so it can actually be accessed by someone that's trying to look through the list. And that's going to be simple too. All we need to do is set cur's next pointer to be equal to our new node. Now 3 is at index 1 and everything is nice and hooked up in our linked list. What if we had done that backwards? What if instead of changing 3's next pointer first, we change 2? Well, now there's no way for us to access 1. The node 1 is completely cut off from us. And if there was anything after 1, it would be completely gone. There's no way to reach it anymore. And Java would just automatically garbage collect it, and we'd lose any valuable data that was stored there. So it's very important whenever you're doing linked list operations to always set the pointers from your new node first, and then change the pointers from the nodes that already exist in the list. Next thing we're going to do is we're going to add something else to the front. So again, when we do an add to front operation, it's really simple. It doesn't matter how many things are in the list. All we need to do is create our new node, set its pointer to the head. Again, very important to do this step first. Set its pointer to the head, and then change the head to point to our new node. And then bam, super fast, constant number of steps, new node added to the front of the linked list. But what if we want to add something to the back of the linked list? What does that look like? Well, in order to reach the back of our linked list, since we don't have a tail pointer, the only way for us to do that is to kind of iterate all the way through. So we start with kind of cur at the head of our linked list, and we're going to just move it forwards node by node until we reach the spot we need to add the new element in. So 4 isn't the end of our linked list, so we iterate forward. 2 is not the end of our linked list, we iterate forward. 3 is not the end of our linked list. And finally, we reach 1, which is the end of our linked list. So we're going to stop here. We're going to create our new node. Normally, we would hook up our new node's pointers first. In this case, its next is only pointing to null, which is usually a default value. And then we set our cur's next pointer to go to our new node. So you'll see, to add something to the front of our list was really easy. We could do that in a constant number of steps. But to add something onto the back of our linked list took iterating through the entire list to do. And that way, it's kind of the opposite of Arraylists, where Arraylists could add things to the back really easily, but to add to the front, we had to do all this shifting. Unfortunately, or fortunately, I guess, unlike Arraylists, we can make this add to back operation a lot faster. You can imagine if we had a tail pointer that was already pointing to the last node in our list, we could have added this 5 onto the end super easily. Basically, no work involved. And that's going to be the main thing we get from including a tail pointer. Now let's do some removals and see how that works. So the first thing we're going to do is we're going to remove from the front. Just like adding to the front was super easy, you can imagine that removing from the front was super easy too. In fact, if we don't want to have to add the data on, or return the data, sorry, then all we need to do in order to remove this first node in the list is this. Change the head pointer forward by 1. That's just a simple head equals head.next. 1 line of code, and then what happens is Java says, okay, look at this 4 node. It's impossible to reach it. Nothing points to it. There's no head pointer. There's no next pointer. Nothing can reach it, and it's just going to get garbage collected. Simple as that, node gets removed from the list. If we wanted to store and return its data, then we would have to do that before moving the head pointer forward, we'd store the data, and then return it afterwards. Unfortunately, removing from the back is not going to be so simple. If we want to do that, just like when we added to the back, we're going to have to start at the head node, iterate by one until we get to the second to last node. I'm going to stress that again. We have to get to the second to last node. And then all we need to do is set the second to last node. That next pointer needs to go to null. It's impossible to reach this 5 anymore, and it becomes garbage collected. Now with add to back, I mentioned that you could make it a lot faster by having a tail pointer, which lets you do the add to back operation in a much faster amount of time. Unfortunately, that does not hold true for remove from back. Remove from back is going to be slow even if you have a tail pointer, because you don't need the last node, you need the second to last node. So, now let's do one more remove. This is going to be an indexed remove. Let's look at removing from index 1. So just like remove from back required us to get to the second to last node, removing at some generic index requires us to get to the node right before the one we want to remove from. So in order to remove index 1, right now that is this node, this 3 right now, in order to remove that, we need to get to index 0. Well, that's really easy. That's just the head. So our iteration would kind of end instantly as soon as we start at the head. Then, in order to remove that, what we're going to do is we're going to set its next pointer kind of forward by 1. So what that line kind of looks like is it looks like cur.next equals cur.next.next. And that's going to essentially skip our pointer forward by 1. So this is cur.next, this is cur.next.next. So we set the pointer like that. And again, just like before, it's now impossible to reach this 3, and it gets garbage collected automatically. Now this is index 1. So the overall actual process of like an add or a remove is relatively simple. It's just a matter of getting to the right place in order to do the operation. That's going to be the big thing in your linked list. I don't think that can happen. Okay. I'm going to take a brief pause just for you guys to ask questions. The other TAs can answer those in the chat. Tyler, I don't know if you see any like big questions that I need to ask, that I need to answer on stream. All right. And from what Landon tells me, the Q&A is going super well. Tons of TAs volunteered to help out with that. Thank you to all of you guys watching and answering the questions. I really appreciate it, especially because it was kind of last minute for me to ask that. But our goal is to make these recitations kind of constantly keep getting better. And I really hope this is better than last week, considering it didn't start with like 8 minutes of bad audio static. Now, with that said, I'm going to go on to the efficiencies. Is this in frame?
Yeah.
All right. So I kind of have two categories for these efficiencies. I've got what if we have a tail pointer in our linked list, and what if we don't have a tail pointer in our linked list. So it's kind of split down the middle right here. So first, let's look at the stuff in the front and the middle. You can imagine whether we have a tail or not, those are going to be the exact same. So adding to the front, as I mentioned before, is super simple. We create a new node, hook it up to the head, and change the head to our new node. Constant number of steps, doesn't matter if we have 1 node or 10 billion nodes. It's really easy to add things onto the front. That's going to be O of 1 time. Now what about removing from the front? Again, as I mentioned, all we do is shift the head forward by 1. No fancy work, just shift head forward by 1. 1 node, 5,000 nodes, always the same. So removing from the front is O of 1 time. What if we want to access the front node? Well, that's just the head. We literally have a variable designed specifically for that purpose. That's obviously going to be O of 1. What about something in the middle? Well, if we want to add something into the middle of our list, we need to traverse up to the spot right before we want to add, then create our new node and set the pointers. So on average, we'd have to traverse about half the nodes in our list, and that's where we get an O of n from, which shouldn't be surprising. We had a similar thing in Arraylists. We can't expect everything to be better in linked lists. Similarly, removing from the front, we need to iterate all the way to that spot right before we're removing from, and that's where we're going to get an O of n from. Now in terms of access, this is where linked lists and array lists are going to really be different. So with array lists, no matter where we tried to access to, it was always O of 1. But in a linked list, as I mentioned, since it's not contiguous in memory, there's no way to kind of jump in a random spot in the middle of the linked list. The only way to get there is going to be iterating all the way up into a specific point and then getting the data. So accessing something in the middle is going to be O of n. But what about the back? If I want to add something onto the back of my linked list, as you can see, if I don't have a tail, I need to iterate all the way up until that last node, then add the new thing on, which is going to be an O of n operation. But if I do have a tail, I can skip that whole iteration step. I can just tack a new node onto the tail, move the tail to set equal to my new node, and I'm done in a constant number of steps. So adding to the back with a tail is O of 1. But what about removing from the back? Removing from the back, as I mentioned, you need to get to that second to last node. So even if I have a tail pointer, even with a tail pointer, it's still going to be O of n. There's no way around that with a singly linked list. And again, access, very straightforward. If I don't have a tail, I need to iterate all the way to it. If I do have a tail, then I have a variable pointing to the back node, and I can get it very easily. So this is our efficiency table. I'm going to give you guys some time to ask questions. First, I'm going to answer the question that someone probably asked already, which is, why would we ever use a singly linked list without a tail if we can just add a tail pointer on and get these improvements? The answer is sometimes we might be using a singly linked list for some specific purpose where we know we're not going to need to use the back of our linked list at all. All of our operations are going to be on the front. And in situations like that, having a tail pointer is just extra memory that has no purpose, essentially. You'll see next week when we talk about stacks and queues an example of something like that. The things I wanted to highlight, how squeaky this marker is I want to highlight this middle access O of n, which is the big difference between array list and linked list. And conversely, I'm going to mention this removing from the front in O of 1 and then adding to the front of O of 1. So array lists had better access in the middle, but linked lists could do better adding and removing at the front. Array lists could do fine adding and removing at the front, or adding and removing at the back. So this is also a difference. Array lists had these two both be O of 1, and although this one was amortized with array lists, versus linked lists have these be O of 1 and array lists have them be O of n. That's kind of some of our big differences between the two data structures. All right, give you guys a little bit of time to write that down, ask questions, make sure that there's nothing I need to handle. Okay, I was told to slow down by an important person, so I will try to do that. We're still pretty good on time right now. Two more things I'm going to get to today, being circular singly linked lists and doubly linked lists. All right. I am going to erase this stuff on the left and work there. What do you have in front? Left side or the right side? Whole thing? Okay, cool. So, next thing we're going to talk about is going to be singly, bad handwriting, circularly linked list. Occasionally, you might see one of us say circular singly linked list. Honestly, I feel like we alternate between which one we say at any given point in time. It's really not that important. The main difference between a singly linked list and a circularly linked list is really simple. Here I have the next pointer on this side just because it makes it easier to write. Not like a previous pointer or anything. That's still a next pointer. So this would be a singly linked list. We've got a head here, and we've got these 3 nodes. All I need to do to make it a circularly linked list is that. Nice big circle. Just means if we start from the last node and go next by 1, we reach the first node again. Now, one big difference is if you remember the code structure I kind of had written over there that started from the head and did while current is not equal to null, that is no longer going to work with the circular linked list, because if you see, if we start from the head and keep going forward, we're never going to reach null. All we're going to do is go back around in a circle over and over again. So what we can do is we can have a code structure that looks kind of like this. We start at the head, then we handle the head edge case, move cur forward by 1, and then our loop looks like this. And now instead of cur is not equal to null, it's going to be while cur is not equal head. And then we move forward by 1 down here. And that's going to be a basic code structure that works with circularly linked lists. Now, just like I mentioned before, if you want to use one with your indices and making sure you don't go past your size variable, that's just fine. That works all the same. But if you're doing that kind of index blind structure I mentioned before, that's not going to work anymore. You're going to need something that looks like that. Important that I use this not equals, and I'm not using like the dot equals method. The dot equals method is value equality, and I might have multiple nodes in my list which have the same value as the head, but this is reference equality. This is checking if it is exactly the same node that head is pointing to, which that is only 1 node in my linked list. So, why would I ever want to do this? You can imagine for like practical purposes, if I have like a playlist or something, it makes sense that kind of the last thing in the list kind of goes back to the front after you keep going. But from like a computer science perspective, what benefit does this give me? Well, I'm going to write a bigger linked list down here to give myself some more room. Because now if I try to do something that was really easy for my old singly linked list, let's say adding to the front of my list, taking a new node, making it the new head. Let's use the same strategy we used with the old singly linked list and see if it works. Well, all I did there is make a new node, set its next pointer to the head, and set the head equal to my new node. Is this a circular linked list? I don't think so. We start going in a circle, but you see the circle doesn't go back to the head. It's a very broken circle. So this is wrong. So it almost seems like we've introduced this circular thing, but now we've broken everything about what makes a linked list good. But that's not entirely true, because we've got some cool tricks that we can use to make this work a lot better. Now, it makes sense when I'm trying to add something to the front of my list to kind of put it here before the old first node. That's the intuition. But with a circular linked list, that's not what we're actually going to do. In order to add to the front, I'm going to make a node here. And again, against your intuition, I'm not going to put the new data in this node. What I'm going to put in this node is I'm going to put a copy of the data from the head. Now what I'm going to do is I'm going to change the data in my head. I'm going to remove it and change it to be equal to my new data. So I've basically swapped the data between the new thing I'm creating and my old head. Now what I do is I set my new node's next to point down here. That's head.next for reference. So again, I can get that really quickly, constant number of steps. And then I set head's next pointer to be equal to my new node. And now you see we have the same 1, 2, 3 in here, but now our new node is at the front of the list, head's pointing to it, and it points into our list, and everything goes nice in a clean circle. This is not like an intuitive thing. Coming up on with this whole trick on your own would be pretty difficult, but we do kind of explain it for you, and we would expect you, if you were coding this on a homework, which you're not this semester, this would be something you could pretty easily implement, and I hope you can see why all this works. Now, what about something like adding to the back of my linked list? With a singly linked list, the only way to add to the back quickly was to use the tail pointer to keep track of that last node, and then just tack something onto the end. But let's see if we can do that in a circularly linked list without having a tail reference at all. So our strategy is going to start off looking really similar to what we did to add to front. We're going to make a new node. Again, after the head, put a copy of the head's data in it, point it to head's next pointer, point head's next pointer to our new thing, and switch our head's data out for whatever we're trying to add. Everything I've done up till now was exactly the same as I did for add to front. You've actually noticed right now I've added 5 to the front of my linked list, but I want to add it to the back. So all I need to do for that is move the head forward by 1. Head equals head.next. Same thing we did to remove the front of our singly linked list. But with a circular singly linked list, it shifts the head forward. And now you see 4 is our head, which it used to be. And if we follow this around in a circle, we now reach 5 at the very end of the list. So we've successfully added 5 to the back in O of 1 time without a tail pointer. So that's pretty cool. Let's look at remove from front. Can we do the same thing we did with a singly linked list? Let's see, we're just making sure we're not losing any efficiency here by switching to a circular structure. Now you should expect it to not be a straightforward operation, just like the add to front and backward. Let's say we want to remove this 4. What I'm going to do is we've already determined that kind of touching this node that the head's already pointing to is very difficult because it screws up the circular structure. So what I'll do is instead of removing this 4, I'm going to remove this node. Now obviously I don't want to lose the data that's in the second node. So what I'll do is I'll copy it into the head. Just copy head.next data back into head.data. And then all I need to do now is head.next equals head.next.next. Now you'll see this node, nothing's pointing to it, so it gets garbage collected. And our linked list now has everything in it just the same, except now it's missing 4. We start at 1 and we loop back around in a circle. So we can do the same add to front, remove from front, and add to back operations, all in O of 1 time, no tail pointer necessary. That's pretty cool. Unfortunately, just like with a singly linked list, there is no way to do remove from back in O of 1 time. The only way to get to this node is to traverse all the way around to the node right before it and remove it just like we would with a regular singly linked list. There's no fast tricks we can use. It's going to be an O of n operation. And also, just like singly linked lists, the regular singly linked list, everything we do on the middle of the list is also going to be O of n for the same reasons it was in a singly linked list. So just to kind of reference back to the efficiency chart, it's going to be exactly the same efficiencies as we had for with a tail. The difference is instead of having a tail pointers using just a slight bit amount of memory, we don't have that at all. We just have a little more complicated operations in order to do everything. I've done all those already. Okay. I think that's good. Is something on like that board going to be too far off center, or is it going to show up fine? I'm just going to use this board because I'm not going to need it again. So next thing we're going to show is doubly linked list. That's the focus of your homework. That's going to be the last thing I really have to focus on in this recitation. But I will take a short break to get a sip of water and make sure that you guys have time to ask questions that TA should be answering. All right, welcome back, everyone. Hope you've enjoyed your short little break. Now we're going to talk about doubly linked lists. So something I want to stress first, because a lot of people tend to get confused when we talk about them back to back. This is not circular. We're dropping the whole circular thing that we talked about previously. This is kind of back to regular singly linked lists, but we're going to change something. Now, instead of just having a data and a next pointer, we're going to introduce a previous pointer, which means that we can now go backwards in our linked list. So if we traverse too far, we can go backwards. And more importantly, when we have a tail pointer, which doubly linked lists pretty much always do, we can start from that tail pointer and go backwards. And that's going to be the biggest difference that determines why people use doubly linked lists. For a little bit of a fun fact, Java's linked list implementation by default is a doubly linked list. Not an expert in like other languages, but I imagine a lot of default linked list implementations use doubly linked lists because they tend to do a lot of operations. They tend to overall be better at the trade-off of some memory that we'll talk about later. Now, a note about doubly linked list operations is since we can go backwards from the tail now, we kind of have a choice. Do we start from the head and iterate forwards, or do we start from the tail and iterate backwards? And we're always going to want to start from whatever end is closer to where we're doing the operation. So for example, if we have like size 20,000 doubly linked list, and we need to add something to index 19,550. We're not going to start from the front and iterate 19,500 nodes. We're going to start from the end and just iterate about 500 backwards. And that's going to be a lot faster. And importantly, if we're trying to add something onto the or if we're trying to remove something from the very end of our linked list, we can now do that really fast, unlike with a singly linked list. So let's make sure I'm not missing anything. Yeah, so something like this, in general, an operation like this isn't going to affect the big O. All of our operations that we do in the middle of a doubly linked list are still O of n. But as I mentioned before, there's a big difference between doing 19,000 operations and doing 500 operations just to add something. So this is kind of a difference where you see practical computation difference, if not asymptotic computation difference. And something like this we are looking for in your homework. We're looking for stuff like this that has significant speedups. Let's do some operations. I'm going to work over here just in case that's not right. So again, we have a head and a tail. And both of them are going to start out pointing to null because we have an empty linked list. Now let's add something. Just like before, when we add a new node to an empty list, all we have to do is put it in with its data, set the head to our new node, and set the tail to our new node. It's very important that you remember to set both. This is actually a little edge case in doubly linked lists. No other time when you're doing add operations will you have to move both the head and the tail, except when you're adding to an empty list. If you'll remember, I mentioned those sentinel nodes earlier. That's actually why people use them, is because it prevents edge cases like this. But on your homework, no sentinel nodes, you have edge cases that you have to deal with. And obviously, these next and previous pointers are just going to start at null because there's nothing for them to point to. It's not circular here or anything, just like that. Now, let's add something onto the front. Let's say we're going to add index 2 to the front of or add data 2 to the front of our list. So, first thing we do is, since we're adding to the front, we should be able to do that operation really fast. We create our new node. A little big. The important thing, just like what I mentioned before, and this is even more important, this can be even more important with doubly linked lists, is you have to remember to set the pointers of the new node before you change the pointers in the existing list. So this means we set our new node's next pointer to be equal to our old head. Our new node's previous pointer is going to always be null because we're adding to the front. Now we set the head's previous pointer to be our new node. And finally, we move the head backwards to point to the new thing we've created. And that has added 2 to the front of our list. Now, just like before, let's add something to the middle of the list. Let's add 3 at index 1. Now, index 1 is essentially right in the middle of our list, so it doesn't really matter whether we start iterating from the front or back. Generally, when you're doing iteration or operations with a doubly linked list, it's more common to go to the index you're operating at. Versus singly linked list, it was really critical that you went right before it. Because you can't go backwards in a singly linked list, but in a doubly linked list, you can kind of go wherever you want. So when I add 3 to index 1, I'm going to start from the tail, because that's close to index 1, which is where I'm going to add 2. So we start here. This is kind of our current node. We're going to create our new node to add. And again, step 1 is hook our new node into the list. So our new node's next pointer is going to be equal to current. And our new node's previous pointer is going to be our current's previous pointer. Now, after our new node is connected, we're going to change the pointers in the existing nodes. So, in this case, it's probably easier to handle current's previous I'm going to be careful when I say this. Current's previous's next pointer. That's the one we're going to change. That's the next pointer of this 2. So we change current's previous next pointer to be equal to our new node. And all that is moving this arrow to be down here like this. Then now, all we do is we set current's previous pointer to be equal to our new node. That one's a little simpler. And it's going to just look like that. And just like that, we've hooked our new node into the linked list. Everything's nice and connected. Just like before, we'll do an add to front with 4. We expect to be able to do this quickly, so let's take a look at it. We create a new node. We set its next pointer to our old head. We set the old head's previous pointer to be our new node. This pointer defaults to null. And then we move our head to be our new node. So adding to the head is really fast. Let's look at adding to the back. Now before, we didn't even have a tail pointer when we do this, but we can expect that with a tail pointer and in a doubly linked list, this should be a really fast operation. We make a new node. No iteration necessary because we have this tail pointer. We hook our new node into the linked list, which is just going to be setting its previous pointer to the old tail. Its next will be null. We set our tail's next pointer to our new node. And finally, we move the tail onto our new node. So almost the exact same steps as we did for adding to the front, just everything's kind of mirrored a little bit to reflect the end of the list. Now let's do some removes. We'll do a remove from the front first, then a remove from the back, and then we'll look at an index remove. So when we remove from the front, it's not quite as simple as it was with the singly linked list. Let's take a look at what happens if all we do is do head equals head.next. Before, this caused 4 to be disconnected from our linked list and it got garbage collected. But now you'll see if we go to the head and do head.previous, that's a way to get to node 4. So it's not going to be garbage collected quite yet. We need to, after moving the head forward, we need to explicitly set head's previous pointer back to null. And now, even though 4 still has a pointer to the linked list, there's no pointer that goes to 4. And it's going to be garbage collected because it's now impossible to reach. So really fast operation to remove from the front. What about remove from the back? In every linked list so far, this has been the slow operation. There's been no way to do this really fast. But let's see if we can do it now. Now, finally, because we have a previous pointer, we can do tail equals tail.previous. We can move the tail backwards, something we couldn't do up until this point. And just like with the head removal, now we just need to set tail's next pointer to go explicitly to null, and that cuts this 5 off from the list. And that allows us to do this remove really fast, all of one time. And that is the big advantage of doubly linked lists. Now let's just do one more remove. I want to remove index 1 from my list. Again, just like I mentioned for add, with doubly linked list, it's more common to iterate exactly to the node you're trying to, the index you're trying to operate on. So we would start either from the head or the tail. It obviously doesn't matter when they're the same distance. We would iterate to this current node. And now, how do we remove it? There's 2 things pointing to this right now. There's 2's next pointer, and there's 1's previous pointer. So those are the 2 things we need to change if we want to remove this node 3. Let's see what those would look like. I would have to do cur.previous.next. That gets me this arrow right here. And I want to set that equal to cur.next. So what that will do is it changes this arrow to point like this. That's one of my 2 arrows down. For reference, that was cur.previous.next equals cur.next. I'm going to mention that because now what we're going to do is cur.next.previous, this arrow right here, is going to be set equal to cur.previous. So that is essentially the exact opposite of what we just did for the first pointer as we're doing for the second pointer, just with all the previouses and next flipped. And that's going to set the pointer like that. Now, even though 3 points to 2 things in our linked list, nothing points to 3, and it gets garbage collected. So you see the lines can kind of get a little weird because they'll have a lot of curs and nexts and previouses in them. But they're going to be, you're generally going to see a lot of symmetric lines, especially when you're doing removes like that. And if you draw it out and diagram it and kind of follow where the pointers are, I find that helps make it a little bit easier and a little bit clearer. All right, I got 15 minutes left. I can get to that extra example if I need to. I feel like we're doing pretty good right now. Let's look at efficiencies. This is in the shot, right? All right. So these were my efficiencies for a singly linked list with and without a tail pointer. Now I'm going to, instead of writing a whole new table, I'm just going to amend this table using green. Does that show up fine on the camera, or is that hard to read? All right, I have a different color. This should show up fine, I think. That looks much better. Right? Cool. So, with a doubly linked list with a tail pointer, the only thing on this table that's going to change is right here. This remove from back is going to become O of 1. Because we are using a doubly linked list with a tail pointer, we can start from the back, we can start from the tail, go backwards, and get to that second to last node in a constant amount of time. Doesn't matter how big our list is. Nothing else on this table is going to change, which means that if we had a doubly linked list without a tail, it wouldn't be any better than having a singly linked list without a tail. And that's why doubly linked lists are going to almost always have tails in them. Because if you don't, you're not really getting any improvement. Versus with a doubly linked list with a tail, you get this faster remove from back operation. Now, people might ask, okay, if you have this doubly linked list that kind of seems objectively better, why would you use a singly linked list? Similar reason I mentioned before. If you know that you're never going to need to remove from the back, maybe you're using an example where you need to add things to the back and remove things from the front, that's always what it's going to be, then there's no real point in having kind of all this extra memory being used up, a previous pointer being added onto every single node in the linked list. There's no real point in that if you're just doing it for an operation that you're never going to use. So if we're going to potentially have to do operations on the back of our linked list other than adding, that's when we might use a doubly linked list, but otherwise singly linked lists can usually do a lot of these tasks just fine. Now, I know some of you guys have asked about this stuff already, but I'm going to kind of explain it in detail here. Array lists versus linked lists. What are the differences? When would we use one over the other? The big thing that we've mentioned so far is access. Specifically, accessing like stuff in the middle. So array lists can always do access in O of 1 time. If I want to get index 4, bam, index 4. Index 27, easy. It's just this really simple, something you'll learn about in 2110. It's this really simple pointer arithmetic operation that gets you to exactly where you're trying to go really fast. I'm just writing any index here. Because obviously, like singly linked lists can access the front and the back just fine, but it's really this any index that we want to focus on. Because trying to access any arbitrary index in a linked list is going to happen in O of n time. because we need to iterate all the way to the index we're trying to go. If we're doing our scavenger hunt, we can't kind of jump straight into the middle of the scavenger hunt. We have to follow the clues one by one to get where we're trying to go. Now, let's say we're trying to do add or remove from the front. Now, with an array list, we have to do a ton of shifting whenever we do something like that. We either need to shift everything down to add our new item or take our item out and shift everything back. So that was an O of n operation. But with linked lists, it's a really fast operation. Whether we have a tail or not, we can do that in O of 1 time. So that's really cool. Now let's look at our back operations. So if I do add or remove from back. I apologize if some of this is a bit hard to read, but I hope you can at least understand what I'm saying. This table should be pretty clear what I'm going through. So array lists, we had add to back being an O of 1 amortized operation for add. But remove was always O of 1. So these operations were fast. With a linked list, we have O of 1, but only for a doubly linked list with a tail. If we're using a singly linked list with a tail, we can do adding an O of 1 time. If we're using, but no matter what kind of singly linked list we're using, removing from the back would always be O of n time. I don't really have enough room to write all of that, unfortunately. Okay. Next is going to be memory format. Gotta look that up. This is memory format down there. So array list is going to be one large chunk. Sometimes we might have to kind of make a new chunk when we need to resize. We kind of get a new piece of memory, but all of the data in our array is always one big thing together. But with a linked list, we have kind of scattered chunks. So you may be wondering, okay, why does this matter? Obviously, I already have the access thing written on here, so why did I write this again? Well, it turns out when people were designing a lot of stuff to run on computers and designing how hardware things would work, they realized that dealing with large contiguous chunks of memory is something that's going to happen really often, and it's something that they should optimize a lot of stuff to run really quickly on. So dealing with large contiguous chunks of memory, computers can do that really fast. They have all these built-in optimizations specifically for dealing with large chunks of memory. And none of those optimizations really work when you have scattered chunks in a linked list. So while it's not going to necessarily show up in any of the big O's, the fact that we're dealing with a large chunk of memory speeds up our operations pretty considerably. And finally, we have memory usage. Now, there's not really like a big way to quantify this, but in general, array lists will be using less memory than linked lists. Now, you may be wondering why. Where does that come from? Because a lot of people think about array list versus linked list memory, and they think, okay, arrays have all this extra space in them potentially before they have to resize, and when you resize, now half your array is essentially empty, versus linked lists always have exactly the amount of space they need. But the issue with that is I'm not really talking about memory like that. When I have an array list, all I have is this giant block that contains exactly all of the data, nothing else associated with it. Versus with a linked list, for every piece of data, I have a node associated with it that also has a next pointer. And if it's a doubly linked list, then I also have a previous pointer. That's kind of 3 pieces of information I need to store for every single piece of data I have, versus array list, for every piece of data, all I need to store is the data. That's the only important thing. So linked lists kind of have a trade-off of they have these scattered chunks of memory that use kind of a little bit more memory overall. And what we get out of it is these operations on both ends being super fast. Now, the real question is that a worth it trade-off over array lists? The answer is in a lot of real-world situations, actually no. Array lists work generally better for a lot of situations, or array-based data structures, I should specify, not necessarily array lists, for reasons that you'll see probably next week when we talk about stacks, queues, and decks. We have little tricks that let us take this O of n and get it down to something much better, while maintaining all of these advantages like using a big chunk of memory and not having to store all these extra pointers. But linked lists can still be useful. Doing these operations on the front and back, maybe if we're dealing with something where we don't know really what we're storing or how many things we're storing, there's a lot of potential uses for linked lists, but array lists do generally have more advantages. Now I only got about 5 minutes left, so I will give you guys some time to ask questions. And then we will go ahead and end it off. Ending it off a little early also helps with the restream having a little bit more free time so that they don't necessarily go over and go past the already really late 7:45 end time. Hello to everyone watching that later time right now, by the way. Hope you're having a good time. For everyone watching this back at 2 times speed later, I hope you enjoy the sound of my sped up voice. So if there's no big questions that you feel like I need to address that weren't already answered by other TAs, then I think we can go ahead and end this off.
Only one has been followed up, and I was going out some homework.
Oh, good. Good question. I should have mentioned that. So homework grades, we've looked at how so in general, in previous semesters, we always try to get homework 1 grades back before homework 2 is due. Unfortunately, this semester with how due dates worked out and how all the situation stuff going on around like coronavirus and everything being online, combined with the fact that this grading on Gradescope is new to most of our TAs, basically everyone that wasn't here over the summer, that's going to slow us down a little bit. So we will almost definitely not have your homework grades back before homework 2 is due. It's really unfortunate, and I am sorry about that. Our current goal that I've set that we're going to try to have all the grades should be back and released next Tuesday, a week from today. It might be a little before then if things get finished early, but it should not be any later than next Tuesday. In general, we will try to have a 1-week turnaround on all your grading deadlines. It's going to be a little hazy in the beginning just because of getting kind of into the gear of things, but that's going to be what we're looking for. Great question. I meant to talk about that.
All right, and then one more I see is recitation worksheets, finding them, and
Okay, so hopefully Neha has uploaded those onto Canvas by now. I think she might be watching this, so if you are, don't forget to do that after recitation. Those will be on Canvas. She might answer. Oh yeah, so I'm talking about recitation worksheets. So recitation worksheets, those will be on the main canvases. So that's the campus and online canvas. Under the file section, I'm not sure exactly what folder. Neha might answer that question with the actual answer. We are not going to release the answers to those worksheets. But if you want to discuss the answers and the problems with NETA, come into office hours, schedule a time, and we're more than happy to talk about it with you guys. But we're not going to be posting those answers on Canvas or something. I think remaining things I'll let the other CAs handle, and I will go ahead